University of North Dakota, and Grand Forks, North Dakota. Just as we let people know, number one, we do have a
Okay, can you hear us now? Okay, you're hanging up. I hate this.
yes.
Okay, they can hear us. Okay.
So Robert's working on how to undo that extremely technical problem. Besides replacing the computer and the but anyway, the show must go on.
Yes. Is over here Robert Moore somewhere?
Feature. As a disclaimer, anything that we say about suggestions, particularly our own personal opinions, not necessarily the opinions of good, governments, FBI, CIA, building, and me, our own opinions. Today we have a very special guest, Dr. Colin Goldblatt, Associate Professor, College at University of up to date. He's at the School of Earth and Sciences at the University of North Dakota and the University of Columbia. Colin, thank you very much for joining us.
My pleasure. It's great to join you today.
Now, hopefully people can hear me. What do you think?
It looks like sound went out.
Okay, great. Well, welcome to British Columbia, at least to Colin at my office. It's nice to be with you today.
Yeah, it looks like things are working other than my camera.
The reason why we have Colin on is because our life was fine. Maybe you want to do that, Colin, like a quick role, like what you're working on?
Yeah, sure, thanks. So, I work on the atmosphere of planets. I'm really an expert on Earth, but also Earth-like planets, because I like to learn about Earth and apply that to other planets in our solar system. What does Earth tell us about Mars or Venus or Titan? But also what do those planets tell us about Earth? And one of my favourite things to study is the long-term evolution of Earth's atmosphere. How has the atmosphere changed over 4.5 billion years of Earth's evolution? And how's that atmosphere co-evolved with life on Earth? And then that's something that can be used to help us understand what an atmosphere on other planets is going to be like, as well as, helping us understand potentially climate change in the context of the past method.
Now, Colin, one of the things I remember early on when we sent a bunch of missions to Mars is this amazing sort of connection that was made ultimately with meteorites that we found in Antarctica and analyzing the composition of the gas pockets that trapped deep inside those meteorites and actually came up with a number where the composition matched the surface of Mars as measured from the local elements.
Yeah, so it's one of the fascinating things about other atmospheres and past atmospheres is how can we find out what is in the atmosphere? And I tell people when I work on past climate, we call that paleoclimate, and people straight away ask, so you work on ice cores then? Because in ice cores we can get bubbles of the atmosphere from the last 800,000 years here on Earth, and that can tell us just what was in the atmosphere. That's some of our best data about past climate. But that record only extends to about one part in 450,000 of Earth history. So getting beyond that is one of the things that's really challenging about understanding past atmosphere.
So how rare or not is extracting gas bubbles from future Earth rocks? Because maybe a measurement of way more than 1 million years ago, we're looking at say the ice core. If you want to go back, I don't know, 100 million years, 200 million years, and so on, then we actually extract the gas back inside of these rocks. And the way you mentioned yesterday, that way, because somehow it gets destroyed in sort of a pressure type of environmental atmosphere.
Yeah. I'd say the answer to that is almost never. I wish I could, it would be easier if I could just tell you it's never, but there are some data that come from bubbles in basaltic rock. So that's volcanic glasses that are erupting in the mid-ocean ridge, and they can bring in little bubbles of seawater. And then from the seawater, you can say, well, these are the dissolved gases in the ocean. And that can tell us a little bit about what the atmospheric composition was at some time. But these are exceptionally difficult measurements to make, and even finding the right rocks isn't very common. We actually use a lot of other indicators, a lot of other things which we call proxy measurements, to tell us about the past atmosphere. I'd be happy to talk about what some of those are.
Well, that would be great to compare a great oscillation that happened on Earth roughly 1.5 billion years ago. Of course, right away, thinking about it, statement. But people are like, well, how do you even know that? There's nobody here on Earth watching that 1.5 billion years ago. And if they were, they didn't leave like an Instagram message somewhere.
Our atmosphere was made up of this.
Yeah.
So how do you scientists know what it was like here on Earth?
So, great oxidation is a wonderful place to start. And I'm going to give the game away and say that the people wandering around on the Earth 2.5 billion years ago, and when I say people, I mean microorganisms here, but let's just give them personhood. They did actually leave a big message saying, this is what the atmosphere is like. I'm going to tell you how. So the great oxidation, about 2.4 billion years ago, the biggest change in atmospheric composition, the biggest change in atmospheric chemistry ever on Earth. And oxygen in the atmosphere went from less than 1 part per million before the great oxidation to around 1% after the great oxidation. Now, oxygen is a super important gas. Wait, I want you to imagine you're dropping an iron nail into the ocean today. What's going to happen to that nail? Does your chemistry change?
Yeah, so it's going to corrode, obviously.
Yeah, it's going to rust. Now, it turns out that how everything behaves when there's different levels of oxygen really changes. If you took that same nail and dropped it in the ocean before the great oxidation, when there's no oxygen, that nail's actually going to dissolve. Because reduced iron when there's no oxygen, is soluble in water. Iron when there's oxygen in that water, it's going to oxidize, it's going to rust. So, depending on whether we have oxygen or not, the chemistry is going to be completely different. So, that's one of the indicators we can find. It's one of the most traditional geological indicators. We start seeing evidence of oxidized iron, that's what we see as rust today, after the great oxidation. We see rocks that are held together with this red iron oxide cement. And we only see them from after the great oxidation. And then there's other things that we see in the record, which we know if there was oxygen, they would dissolve. But we actually find little pebbles, for example, of uranium ore in the rock, in river sediments. Now you put that in a river today, it's going to dissolve because there's oxygen. But uranium ore is not dissolved when there's no oxygen. Iron dissolves when there's no oxygen.
But,
so if we go back into the geologic record, look at the rocks, we can say, did this rock get deposited when there's oxygen, or did it get deposited when there's no oxygen? And there's just this change that happened really suddenly 2.4 billion years ago.
Now, of course, the big question is, why did that change occur? In fact, because it could have happened again today sometime.
Yeah, absolutely. So there's a couple of reasons why it occurred. And one of those reasons is about biology, and the other is about chemistry. So I'm guessing you two guys are physicists, so you're probably terrified at this point. You push back to biology, Carl.
Actually, my second master's was done at Case Western as a geologist, as a planetary scientist. So
okay,
I'm following along well.
You're okay, Robert. Hopefully you're surviving the flame. Okay, you know, I like to tell our students when I teach them at second year that, you know, we're studying earth science, we're studying climate science. That's really difficult. If they want something easy, they can go over the physics. You know, we even know the equations for most of the physics. So,
very
true.
Talk
about why is oxygen. Every scrap of oxygen in our atmosphere today is a biological product. It is produced by photosynthesis. And that photosynthesis is where organisms, that can be trees and plants on the land, or it can be cyanobacteria in the ocean, they're going to make their energy from sunlight. And they're going to use carbon dioxide, they're going to use water, and they're going to use the sunlight to fix those into sugar. And then there is a toxic waste product from that. And like anyone who's cheaping out, they're just putting that toxic waste product straight into the atmosphere. And that's, of course, the oxygen.
Right.
Oxygen is the toxic waste product of photosynthesis. But this is the really interesting thing. If we know the organisms that do that photosynthesis, they evolved, I'm going to say, 3 billion years ago. So they're humming along in the ocean, and it was mostly in the ocean in those days, and they're producing oxygen. But it's just not getting a drift in the atmosphere. The levels rise to parts per million, maybe 10 parts per million, but they get stuck there for a while. And the reason for that is that as well as producing oxygen, well, that organic matter is getting decomposed, but without oxygen, because the atmosphere levels are low, it's getting decomposed by a kind of organism called methanogens. They're making methane. Today we don't get a lot of methanogens. They only live in environments with no oxygen, like cow's guts and termites and rice paddies. But they're producing the methane. And in the atmosphere, the methane and oxygen are reacting. So that's keeping the oxygen levels low. So in order for oxygen to build up, we need to make that reaction rate between the methane and the oxygen quite inefficient. It's going on really well in the early Earth, but we need to slow it down. And then what do we do to slow it down? Well, we build the ozone layer. And that is the real key to the great oxidation. We build the ozone layer, and that slows down the reaction, and it lets oxygen build up to percent level.
You're affecting the amount of ultraviolet light from why it slow down that reaction.
Yeah, absolutely. Because all of the chemistry in the atmosphere is mediated by UV light. And UV light is going to ionize some of our molecules in the atmosphere, then they're a lot better at reacting, and then they really get going. So one of the first things that we're going to ionize is the oxygen, and then that allows us to build up ozone. So a process called the Chapman cycle, something we study in an atmospheric chemistry class, use oxygen to build ozone. And once we build up that ozone, that's going to block the UV photons high up in the atmosphere. They can't get low down into the atmosphere. That slows down the rest of the chemistry.
Now, when you say that the great oxygen event happened suddenly, what do you mean suddenly in terms of years?
Yeah, so geologically suddenly, that means it probably took, I'm going to say, between 1,000 years and 10,000 years.
Oh, so that is sudden.
Yeah, that's the blink of an eye.
Wow.
Yeah. It's
why would this happen? Why did it happen at the time it did?
Yeah, so it turns out you've just got to build up just enough oxygen in the atmosphere. And if you've got other things that react with the oxygen, that could be gases from volcanoes, for example, volcanoes put out all kinds of nasty stuff that reacts with oxygen. So if you've got other things that are putting out just enough stuff that reacts with oxygen, it can keep the oxygen down. But once oxygen builds up to about 10 parts per million in the atmosphere, then we get something we call a tipping point. And oxygen builds up, and it's starting to build up, means that it builds up quicker. That's something any of your listeners can try at home. If you're sitting on a dining room chair, just try leaning back until the point at which you balance, then lean back a little bit more and get your head on the floor.
Figuratively, don't try this at home.
Yeah, I'd just like to say that message actually came to you from the President of France. It was not from the University of Victoria. So that's an example of a tipping point. Your chair, your dining room chair, has got two different stable states. It's got the state that you should be sitting in right now. Then there's that unstable state where you balance it on its two back legs and you think you're big and clever. And then you fall over and your chair's got another stable state, which is you're lying on your back, the chair's not moving, and you're getting a telling off from your parents, spouse, or whoever it is.
Now that's very...
That's just the way the emergency works.
But that's very scary, not from the point of view getting concussion, but from the point of view that you can rapid, hugely changes in our atmosphere over a very short period of time. And I immediately think of human effector atmosphere. That the Earth is so large, how could we, having open fire, do anything to the atmosphere? And it builds up over time, and all of a sudden, boom, and
bam.
Yeah, and that's, I think, one of the most fun things about atmospheric science and climate science is that, well, my favourite branch of mathematics is dynamic description theory. And that's the branch of math that tells us how things change over time. And what we learn is that we can have gradual and smooth change, but we can also have really rapid change and changes between different stable states.
So, kind of getting into breaking it down, we've got local minima and maxima, we've got global minima and maxima, and we've got metastable states.
Yeah. So I want to give an example, and this is an example from Earth's recent past climate, is we've been cycling between ice ages and interglaciers, which is what we're in now, and we've been cycling between enough ice to cover all of Canada, like you say, with a kilometre deep here, and then I think in the Dakotas, you're just beyond the ice front there. So 20,000 years ago, we had a kilometre of ice covering us here. And then that melted really rapidly about 13,000 years ago. Um, but we've been cycling between ice age integration, ice age integration, back and forth over a number of cycles. That's an example of that kind of dynamical behavior. And if we go to a warming world, which we all know we're going to, we're going to come to a point where it gets too hot for Greenland to survive. And then over maybe 500 years, there's going to be a rapid melt of Greenland. And then it's gone. It's not coming back. We've moved from the stable state. Okay. So this is really how the atmosphere works, how the climate system works. We have gradual change, but then we hit a tipping point and it happens quick.
You obviously sometimes, whatever, that, it's okay to decide to always being right away. That's not always true. Those are, I think, years from now,
yeah. Being a scientist in the movie is way more glamorous than being a scientist in real life.
Probably pays more money too, yeah.
Yeah, and a scientist in the movie, like a regular 10 minutes of their time is like the 10 best minutes of my job of my entire lifetime, all crammed into one. And they're much more powerful because they seem to be able to bend the laws of physics, which I'm not allowed to do. It's part of my contract. So, yeah, we're doing these big experiments with the climate, and what's going to happen? How much do we understand that?
Well, I went to your webpage and I looked at some of what you're doing or have done, and I like the fact that you mentioned in there that you studied cloud cover, because water vapor is a greenhouse gas. Clouds are reflective. Or are they?
Yeah. Clouds are one of the most fascinating bits of the climate system. I'm going to say, hopefully anyone can look out the window and see some clouds. I'm going to say here, in Victorian British Columbia, we hardly have any clouds. Victoria is a great place to live in the summer. Please come and support our economy here. We love you. We have very little clouds. It's beautiful and sunny. But clouds do two things. They reflect sunlight. We all know that. It's cloudy, it's very sunny. But they also have a greenhouse effect. And you'll know that from at night. If it's cloudy, it tends to be a warmer night than if it's a clear night. So clouds have these two competing effects. They've got a greenhouse effect, which helps keep us warm, and they reflect sunlight, and that helps keep us cool. And these two effects play off each other. At different times in different Earth histories, different things have different importance. So right now, the reflection effect of clouds is much, much more important. If you took the clouds away, Earth would heat up a lot. It would be a bad day. So, when we need a bad science moving, it's going to be, there's going to be some new organism that eats clouds. And it's going to eat all those clouds, and, we're starting to get very hot very quickly. But we can also look at different times in the history of Earth and say, well, let's say early in Earth history, there was less sunlight because the sun was less bright then. Actually, let's take a digression on that if we can.
Okay.
This is something called the faint young sun problem. I think if you've ever had a stellar physicist on your show, they'll have told you that main sequence stars like the sun get brighter as they age. Like professors, really. We get smarter as we get older.
Hopefully.
The sun gets brighter as it gets older. Now, if the sun had got brighter and the atmosphere hadn't changed, that would mean that early in Earth's history it would be much colder. But actually the evidence is that early in Earth's history it was probably warmer than it is now. And that, Carl Sagan calls that the faint young sun problem. Then what Carl said is, well, the answer to this has to be that there is a stronger greenhouse effect in the past. And what Carl suggested was that the best greenhouse to use for that would have been ammonia, because there's a reduced atmosphere, there's no oxygen, that's what we've been talking about earlier, so maybe ammonia could survive in that atmosphere. And ammonia absorbs thermal radiation just where water vapor doesn't absorb it. So if you want to make the best greenhouse you can, use a mix of water and ammonia.
Did not know that.
Yeah. Now, everyone can now forget part of what I told you because it turns out ammonia doesn't work. And the reason it doesn't work is it dissolves in the ocean really well. Ammonia is really soluble. If anyone's ever heard of Windex, they might know why. And the other thing is it gets zapped by photons. It's really photochemically unstable. So every scientist who's worked on this problem has tried to figure out a way of making ammonia work. And we've all tried. I tried. I failed.
Is there something other than ammonia that you can try?
Yeah, so the most important thing is carbon dioxide. Because carbon dioxide is a pretty good greenhouse gas and it's really stable in the atmosphere. And we've also got lots of carbon and we've got lots of oxygen. So the main part of the solution to the failure of the sun is that we had much more carbon dioxide in the atmosphere when the sun was dimmer. So let's say the sun was 20% less dim 2 billion years ago. We're going to have 30,000 parts per million of carbon dioxide in the atmosphere. 3% carbon dioxide.
Oh, wow.
In order to keep us warm.
That's a problem.
Well, it'd be a problem now that the sun is brighter, but back then, it's not a problem. It's just what happened.
Well, I was thinking more in terms of how do you get that much CO2 into the atmosphere and where did it go?
Yeah.
Oh, right. It's much more geologically active than that. Yeah.
So let's stick with that actually. Carbon cycle is really fun to talk about. So let's use some comparative climatology examples. So how much of an atmosphere does Venus have? You guys know about that? You guys know?
Yeah. Quite a bit. Yeah.
How much is quite a bit?
The pressure
Yeah, tell me about
is
pressure.
Yeah, so we touched the water. 9
something
Yeah,
like that.
it's 90 times the pressure of
Yeah.
Earth. And Venus is about the same size as Earth. Let's just say that's 90 times more atmosphere than Earth. And what's that atmosphere?
Primarily nitrogen, isn't it? Carbon dioxide.
Well, guys, you're going to have to come back to class for fancy
Yes.
It's got, so that 90 bars of Venus' atmosphere is 97.5% carbon dioxide and
Okay.
3.5% nitrogen. So
Okay.
that's about 3 times as much nitrogen as on Earth, but way more times carbon dioxide than in Earth's atmosphere. So the question,
Yeah.
so Venus is on a crazy Venus, crazy. So the question isn't why has Venus got so much, but why has Earth got so little?
And that's where I was going with my wow at 3% carbon dioxide.
Yeah.
Where did it go?
Yeah. Show guys where it went?
Went to carbonates, probably. Dolomite and so forth.
Yeah. So this is a bit of carbonate rock, which is probably a dolomite. This particular bit of rock is about 700 million years old. I'll tell you a bit more about it later. But it's a carbonate rock. We've taken CO2 out of the atmosphere and we've put it in the rock. And here's the cool thing here. If you can see the little structure on the rock here, that it's got these shapes on here. Things like that don't grow by themselves. That's actually biology's done that. This is a fossil stromatolite, which is a kind of mat organism that can facilitate calcium carbonate precipitation. So we put all our CO2 into the rock, but all of that has been mediated by biology.
Okay.
Wow, isn't that cool?
That's cool.
So,
Here's a question.
yeah,
Is there anything that we can do that accidentally reduce the amount of that? Yeah.
Or not so accidentally do.
yeah. Well, so with that chemistry class here, so the fun thing about carbon is that there's really two different carbon types. There's an oxidized carbon type, so that is taking CO2 and using putting it into calcium carbonate rock. And then if you get back into the atmosphere, traditionally you conduct those calcium carbonate rocks, you heat them up in a production zone, they'll come back out of volcanoes.
Okay.
We've got a modern way of doing it.
Yeah.
And that modern way is called cement manufacture.
Yes.
Yeah.
Forgot about that way. Yeah.
Yeah. So that's the stuff about carbon dioxide emissions today. The way you make concrete is you get some cement. And how do you get that cement? You take limestone rock and you put it in a limestone. That limestone, you heat it up until that until the calcium carbonate breaks down.
Yeah.
And you get lime, calcium oxide, and you get carbon dioxide. And like those cyanobacteria, they just put that toxic waste in the atmosphere. So that's one of our carbon cycles, but the other carbon cycle is organic carbon. So photosynthesis will fix carbon, put carbon dioxide out of the atmosphere with water from the ocean, and it will make organic carbon. And most of that, so that's you and me, all the listeners, we're all made out of organic carbon, and most of that we have a really quick cycle. We produce it with photosynthesis, but then, that photosynthesis, well, that's going to form let's say some nice leafy greens. We're going to eat them for our lunch. We're going to respire it, and we're going to emit that carbon dioxide again. So most of it is really rapid closed cycle. But just one little bit of that organic carbon, I think it's 0.1%, can get buried into the rocks every year. A little bit of it, we don't eat for our lunch, nothing eats for lunch, and it's going to get buried in the rock. So that is a very long-term carbon source. Incidentally, that can help accumulate oxygen in the atmosphere because we bury the carbon, we don't use the oxygen when we're respiring it. And then that buried organic carbon, a small fraction of the total buried organic carbon, you can make money off digging it up and burning it. And the stuff that we can make money off digging it up and burn it, we call it fossil fuel.
Right.
And that's the big way that we're putting CO2 in the atmosphere today, is burning 120-million-year-old dead bugs from the bottom of the ocean.
Now, Colin, on Earth, we're not making because of the carbon reduced a lot. So why didn't that happen on Venus?
Yeah, that's awesome. If I had a time capsule, I would answer that question perfectly well. So, Venus, we're going to have to talk a bit more about atmospheric physics here. We're going to have a break from chemistry. Actually, I'll just say here, if anyone who finds chemistry a bit weird, I've never had a university level chemistry class. I was a meteorology major at college, meteorology and oceanography. And I didn't think I needed to learn any chemistry until I started working on Earth evolution.
Yeah, I was.
Let's do some adult education here.
Yeah, I was studying Earth interior, and I know exactly what you mean. I only needed that basic chemistry until then.
Yeah. So I had to learn a lot of chemistry as an adult. So anyone who's doesn't like one of the branches of science, not too late for you. So something happened on Venus call a runaway greenhouse. And it's another example of a tipping point in the atmosphere. So what I'd like everyone to do is imagine that you turn the taps on your bath and you let the plug hole open, the water will fill up a bit to a level at which the amount of water coming in to the tap is equal to the amount that's going out through the plug hole. And you make the plug hole a bit smaller, you'll need to build up more water in the bathtub to get enough pressure to force that water out of the plug hole.
So dynamical equilibrium.
Dynamical equilibrium. Now, you make that plug hole really, really small, what's the dynamical equilibrium going to be?
Water all over your floor.
Yeah, exactly. So, same kind of thing can happen in the atmosphere of a planet that has water in its atmosphere. So any planet that's got an ocean, the amount of water in the atmosphere is going to depend on the planet's temperature. Because we turn the temperature up, we evaporate more water into the atmosphere. So water vapor is a super good greenhouse gas. It's the best greenhouse gas. Well, water and carbon dioxide together, they're really good, they work in slightly different ways. But if we build up enough water in the atmosphere, it turns out we get to a limit on how much radiation we can get out of the top of the atmosphere. When I say radiation, I mean how much thermal radiation we can get out. And if we turn the sun up enough so that you're just one little bit more sunlight getting absorbed than that maximum on the amount of radiation that you can get out, then you're going to go into uncontrolled heating of the planet.
Right.
And we call that a runaway greenhouse.
So that's, just for people to kind of think about it. So in the daytime, the sun's trying to reach the earth, the sun is the brightest and the middle of the opposite spectrum of the light on this part of the system. And that light on a clear day then heat up the surface of the earth. But at night, those blocks and stuff will be not be going in and infrared much longer wavelengths. And those are the types of photons that if you interact with this block more, the water vapor is carbon dioxide, it's almost like the chemical material. The more opaque the atmosphere, the more you have of that water vapor and carbon dioxide. You can't get that radiation out. And that energy is
Trapped inside. Yeah.
Yeah. So, let's just go back a step. We need a greenhouse effect. Without a greenhouse effect, it would be way too cold. Yeah. It would be worse than Northern Canada in the winter.
Think of the habitability zone.
Yeah.
Ultimately, we can try this in and when you think of life elsewhere, that really depends, what you're saying here, on the atmosphere composition at 100%, because that is just the habitability zone. Where would be the just right temperature from the whole sun? That would be greatly affected by the makeup of the planet itself.
Yeah, so let's hold that thought for a minute. I want to come back to that. But let's just finish off with the runaway greenhouse here. So we've got a greenhouse effect. We need enough of the greenhouse effect to keep us warm, but we make it too warm, we get too much water in the atmosphere, and we hit the runaway greenhouse. And we'll talk about that as an inner edge of the habitable zone in a minute. So we think that's what happened to Venus in the past. And why would that happen to Venus but not Earth? Well, because Venus is nearer to the sun than we are. So it's getting more sunlight than we are, just like it's closer to the campfire.
Right.
So in fact, we don't know whether Venus ever condensed an ocean and then experienced a runaway greenhouse, or whether Venus has never condensed an ocean in the first place. But it went through the runaway greenhouse. If there were any carbonate rocks, they'd have been baked off just like they're in the limestone. So, yeah.
Yeah. And with nowhere to go now because there's no water.
Yeah. So that I'm going to break this news to listeners here. The end of the world, when it comes on Earth, will be a runaway greenhouse lime kiln and furnace.
Right.
That's not going to happen for 500 million years, maybe a billion years. That's our best guess. So don't worry about today. You know, don't forget Cyclone 50 next week. The end of the world is not coming.
So just to kind of drill down a little bit on the so if Venus didn't have large quantities of water, because even the subject of where does the water ultimately come from is a question. And you speculating in one of the comments or passages about that, and others, in different directions on that issue. So if Venus never had a substantially large amount of water, then basically its carbon dioxide would be everything.
One of the great things that we said is spacecraft to Venus. So one of the things we've been able to do is measure some of the isotopes in Venus's atmosphere. So isotopes, what am I talking about here? So these are the same element, but with different atomic weights. So, our normal water, so our normal hydrogen, that's going to have one proton, one neutron in the nucleus. So we can get a heavy hydrogen atom, which has got the same one proton, that's why it's hydrogen, but it's got two neutrons. We call that heavy hydrogen or deuterium. And that's got the same chemical properties, different physical properties. And what we found on Venus is that Venus is really enriched in that heavy hydrogen. So that means that it's lost the light hydrogen. How does it lose that? Well, it loses it to space. And the only way you can lose hydrogen to space is by getting a lot of water vapor high in the atmosphere.
Right. Okay.
So we know Venus has the water because we can see the evidence of it moving the water.
Right. That's really good point. Yeah.
Well, if it's more than water itself, why would it have to do it only with some kind of planetary impact within the solar system? Why would it happen in the solar system?
Venus is our twin. If you look at Venus and think Venus is what happens if you don't do the homework. Don't do the homework, you end up like Venus slightly close to the sun. But it's also our future. Because the sun...
Now, Carl, if I had gave you a very large budget,
please.
what would you do with it in terms of looking at the different communities and different commanders on the surface of Venus that could analyze the rock or even bring it back to better study here in Earth?
I think what I want to do is study the noble gases in Venus's atmosphere. Because the noble gases show you much chemistry. And some of them have got a bunch of different isotopes. So by learning about the noble gases, we can learn about a lot of geologic processes, a lot of escape processes, just by taking a sample of the atmosphere. So that means that a really big budget I can still do it without an insane budget. So I'm going to go for a mass spectrometer which can measure every isotope of every noble gas on Venus.
So we're closest to the sun of the Earth. So if we expect that some of that noble gas will reach its velocity until you have sort of speed by and get it from the surface of Venus over time, how would that work?
Well, the thing with the noble gases is they don't like getting in there. They really just like being in the atmosphere, so they're going to hang out in the atmosphere. They'll make them easy to come. There's some which are actually produced by the rock. So, for example, argon, it's got two isotopes. It's got argon 36, that's been around forever. But argon 40, which is a radioactive decay product of potassium 40. And potassium is in the rock. So if we find less argon-40 than we might expect on Venus, what it means is that Venus hasn't been outgassing very well. The volcanoes aren't very effective, or the mantle isn't mixing. So just from that atmospheric sample, we could say some things about the geology as well.
Yeah, because we know that Venus, for example, doesn't have a plate like the Earth.
Yeah, so Venus tectonics is kind of weird. It looks like there was a big resurfacing maybe 700 million years ago, but it's not a plate system like we are. It's probably an episodic tectonic system, so tectonic turns on and off. Whereas Earth, continuous episodic tectonics, gonna do it when it feels like, isn't it?
Yeah, it's like a pressure cooker lid. You know, you build up the pressure too much, it whoops.
Yeah, exactly. Turn up the pressure inside, turn up the temperature. Wow, we've got plate tectonics again.
Right.
And I know from like examinations down the radar, studies evidence for over 20,000 different volcanoes in the system.
Yeah. And one of the other things is these all tie in, because one of the things that helps lubricate the mantle on Earth is water. And we get water from the ocean into the production zone into the mantle. So we lubricate our mantle real nice on Earth, but on Venus we've lost that water. So we're not lubricating the mantle as well. So that's going to be a problem for plate tectonics. That's going to mean that we can't cycle rock in the same way. That's going to affect the atmosphere. This is the big story in atmospheric evolution. We talked about biology first, then we talked about some chemistry, then we talked about some geology. All of these different things put a signal in the atmosphere. So studying atmospheric evolution, you need to know a little bit about all the branches of science, and you need to know how to talk to people who work on all those different branches of science.
I mean, physics, like you alluded to already, is the fundamental science, and therefore it makes it easy because you don't really, when you take the systems up as tight and complex, you go down to the building blocks, and that's what we do. So stuff that you feel like, well, you can't make it less complex than something bigger.
Right.
And so you're always doing it tight and complex systems.
I've had this discussion with you, Wayne, that I never realized how contrived our physics experiments are, because we can contrive them down to changing one thing, but in a geological or atmospheric setting, you've got all these things changing, and there's nothing you can do about it.
I think the only thing more complicated than atmospheric evolution is maybe ecology.
Oh, yeah.
We've got some hope of writing down equations for atmospheric evolution, but we really don't understand the ecology well enough. And that's actually important, because life is one of the things that has the biggest impact on the atmosphere.
Right.
And we don't understand it at the level that we'd like to. So that, I think, is the cutting edge in understanding atmospheric evolution, is understanding why does life have the effects that it does. Can we understand that from any kind of predictive perspective rather than just a descriptive perspective?
Where did life even come from? Start back into the beginning. Right. And you go from something abiotic
to biotic. Let's face it, what are we all aiming for? What kind of signatures are we looking for that say, hey, there's life way out over there?
Yeah, so basically, I probably want to say something about what it means to spend planet. And I hope we have to be able to remotely confer that with biology.
Yeah, so I want to go right back to the Viking program to start with that. And the Viking program is going to send some missiles to Mars and look for life. And it turns out that my PhD supervisor got hired to work on the Viking program, and his name was James Lovelock. And he was actually kind of mainly an instrument builder, and he was supposed to be working on how we're going to detect life, what are we going to do on that. And And then he had a collaboration there with a woman called Jan Hitchcock. And they came up with the idea that to look for life, actually the best way is to look in the atmosphere. Because that is where life puts all its waste products, is in the atmosphere. So if we take a systems perspective of this, you want to look for life. Don't put out little taps looking for bugs to trap. Just look at the atmosphere. If there's abundant life, it's going to show its signals in the atmosphere. So Jan Hitchcock and Barkhouse published a paper talking about life detection by atmospheric analysis. And that really set the scene for everything that we know about in exoplanet life detection, because all we can do is point a telescope at those planets. We can't send a lander to a planet in another star system. Not in our lifetime, not in our children's lifetime can we do that. So we're going to point a telescope, we're going to look at the spectrum, and we're going to try to figure out what gases we have in the atmosphere. And what Jan Hitchcock, James Lovelock realised, which is so profound, if you look at the atmosphere of Venus, it's in chemical equilibrium. You look at the atmosphere of Mars, it's in chemical equilibrium. That means those planets aren't pure. You look at the atmosphere of Earth, the atmosphere is in profound chemical disequilibrium. And the way that we do that is we keep putting clusters of different gases in. We put oxygen in from the biosphere, we put methane in from the biosphere. It takes them 10 years to react with each other, but we keep putting them in. We can always get oxygen and methane in the atmosphere. You notice that pair of oxygen and methane, they should have annihilated each other. You observe them together, and you've got no other way of explaining it, then that's got to be life. So that's how we do life detection by atmospheric analysis. The only way to really do it properly is you've got to look for disequilibrium in the atmosphere.
It's like the Sherlock Holmes.
So there's not one key gas or gases we're looking for. It's that combination of that cocktail.
Yeah,
says,
I'm one of the people who's really kind of hard about this. I'm saying that every gas that you can think of, that you might say is a biomass of oxygen. Well, I can find you ways of making oxygen without biology. So methane, I can find you ways of making methane without biology. Almost everything you can find a way of making it without biology. So the more information you have, the better the spectrum you can get, which really means the bigger the telescope you can build. Building the biggest space telescope you can. let's have a 2-kilometer mirror space telescope. And let's see what
I'm
we
with
can
you.
find out.
I'm with you.
Yeah, let's just take the entire military budget and use it on space telescopes instead.
Right.
For 1 year.
Yeah.
But here, what you're looking at is signal to noise. We're trying to extract signals of these different molecules that we have. And this is a sampling field level, and that would depend on the abundance of signal source. And sampling down to a reasonable level that we can take it to people to be able to say yes or no, there's something interesting going on this planet.
Yeah. And one of the things is some of that spectroscopy can be really tricky because different molecules, you know, they don't hold up a calling card saying, hi, I'm Wayne or I'm Colin. They absorb at different wavelengths, and then you've got to figure out, well, which is which? What combination of gases do I have? So, yeah, the more signal and noise you can get, the better. The more photons you can get from another planet, the better we're going to be able to calculate.
I guess we got some audio.
I'm thinking, it sounds like we've still got audio issues.
Oh. Well, we've been having a nice chat, guys. I don't know if the audience has been tuning in, but I've been enjoying myself.
Yeah, I think it was signal to noise.
Yeah, the signal to noise is clearly.
maybe we can get you back and bring the final.
Yeah, if it turns out to be noise over signal, then we'll go back and do it again and talk about something totally different.
No, that'd be cool if we could do that. So, do you want to end it here, Robert?
Yeah. Let's try to end it here. I hate it doing it, but
Yeah, so we'll just say that, if people are interested in this type of studies, I mean, there's lots of opportunity to learn more. You go to higher education, learn about chemistry, atmospheric sciences, how
I'm still here.
so thanks a lot. So, bye, everybody.